Question 1, we have these two isotopes of boron, and it tells us that's the relative atomic mass, which remember is the weighted mean mass of an atom. So we can straight away rule out A and B because that number is much closer to 11 than to 10, which tells you that you've mostly got 11. So 8% or 20% of 11 is clearly a non-starter. So it's got to be C or D. You could guess one and do the calculation. You could do some algebra and actually calculate it, but both of those things potentially would take too long. Remember, you're not going to be spending more than 1 minute per question on these multiple choice ones. So the quick way to do it is just to think of it as a number line. Right, if you've got 10 there and 11 there, 10.8 is obviously 80% of the way over towards 11, and therefore you've got 80% of boron 11. So the answer is C for that one. Question 2 is a straightforward oxidation state question, so long as you remember that when you have ions you can just treat them as separate entities and use the oxidation state rules separately within one and the other. So here we've got two lots of -1 because it tells us chlorine is -1. So to get from -2 to +1, you can immediately deduce the iodine is +3. And then for this one we've got 6 lots of -1. And again, to get from -6 to -1, which is the overall charge on that ion, the antimony is +5. Okay, so +3, +5 is the right combination, and so the answer is C. Question 3 wants us to find out how many individual hydrogen atoms there are in 0.125 moles of ethanol. So the first thing to register is that each molecule of ethanol contains 6 hydrogen atoms. So therefore the moles of hydrogen atoms is equal to 6 times the moles of the compound as a whole. So 6 times 0.125 moles, which is 0.75 moles of hydrogen atoms. And then we simply use the idea that the number of atoms is moles times Avogadro's number, which is one of those fundamental relationships of moles that you need to know. So we just multiply that number by 6.02 times 10 to the 23, and you get 4.515 times 10 to the 23, which is answer B. Right, question 4, we've got this titration information and it wants to know the concentration of the nitric acid. So as always in any kind of calculation like this, we need an equation for the reaction. So it's just acid plus hydroxide goes to salt plus water. You've just got to make sure you get the formulae of the compounds right, but it's helped you by giving you barium hydroxide. So we've got barium hydroxide plus nitric acid, and obviously barium's 2+. If you'd forgotten that, then that formula tells you that anyway. So barium nitrate is going to be BaNO3 twice, and then water's the other product. And to balance that, well, obviously 2 nitric acids means you're going to have 2 nitrates here, rather means you've got to have 2 nitric acids there, and that also means you have 2 waters. So that's your equation, but the only bit that really matters about that is that the moles of nitric acid is twice as much as the moles of barium hydroxide. So okay, now let's get the moles of barium hydroxide. So we get moles is equal to concentration times volume in dm cubed, which is 0.0450 times 0.0250. Okay, so those are the numbers from there, just remembering that you have to convert from cm cubed into dm cubed. So 0.045 times 0.025 equals 0.00125 moles. And then we've got to multiply that by 2, because that's what the equation tells you. So times 2 is equal to 0.00225 moles of HNO3. And then we've got the moles, we've got the volume, so we can just do concentration is moles over volume, which is 0.00225 divided by 23.35 cm cubed is 0.0 0.2335, which gives us 0.0964 moles per dm cubed, which is answer D. So that's the correct one. Question 5. If we're comparing the ionisation energies of nitrogen and oxygen, then what we're talking about is trend across a period, and in particular, if you remember that trend, we're talking about the second blip in the trend, where the overall increase across a period gets reversed. And that one, remember, is because in nitrogen you have 3 unpaired p electrons, because it's 2p3, but in oxygen you have a couple of paired ones, because it's 2p4. So the way you would normally explain it is in those terms, by saying that the paired electrons are easier to ionise than the unpaired ones. But of course, the reason you give for that is because there's stronger repulsion between the paired p electrons than the unpaired ones that nitrogen has, and therefore that fits, in fact, with answer A, is the one that fits closer. It's not to do with nuclear charge, so it's not B. It's definitely 2p rather than 2s in both cases, so it's not C. And whether the overall number of electrons is odd nor even is neither here nor there. It's the pairing that matters, so A is the only one that fits for that. Okay, so question 6. We've got this information and we're asked what's the formula of a compound that will be formed between X and Y. So if X is in group 2, you know that what it does is form 2 plus ions. If Y is in group 5, this alternative nomenclature, 5 or 15, obviously that just depends on whether you take account of the 10 sort of little groups within the transition elements or not. Both of those are labelled on your periodic table if you look, so there shouldn't be any confusion there. So we're talking about group 5 elements, which means 5 electrons in the outer shell. That means they need to gain 3 more to reach 8, which is what nonmetals do when they form ions. So it's going to form a 3- ion. So those are the ions you've got, and to balance up the charges you obviously need 3 of those and 2 of those, so it's going to be X3, Y2 to make the charges balance, and that's answer C for that one. Question 7 about ammonium carbonate is one of those where it pays just to scan the answers quickly before you even start thinking in detail, because D, which gives you the formula, is clearly wrong, because you know that ammonium is NH4+, you know that carbonate is CO3 2-. So provided you've memorised those ions, which hopefully by now are secure in your brain, then you know that the formula's got to be NH4 twice CO3, and therefore D is wrong, so D is the answer. The other ones, A is correct because remember that barium sulfate is insoluble. That's how the barium carbonate is insoluble. That's why when you do the qualitative analysis things, you have to do the carbonate test before the sulfate test, because otherwise you'd get a false positive when you add barium nitrate, because it will precipitate carbonate or sulfate. So you're supposed to sort of know that as background knowledge for qualitative analysis. Effervescence with acid, well, that obviously is correct for a carbonate. And the alkaline gas with sodium hydroxide, that's the test for ammonium, so that's clearly true as well. So therefore D was the right answer, but you could spot that actually straight away without even thinking about the other ones. Question 8 is about concentration versus, rate versus concentration graphs. So we've got rate on this axis and concentration of X on this axis, and it's told us it's first order, so that's the rate equation, and that just tells you that it's a straight line. Okay, so rate is directly proportional to the concentration of X, so it's just a straight line going like that, and therefore the answer is A. So you need to remember those graphs. Remember, if it had been 0 order, the rate would have been independent of X, so it would have been a flat line like that. If it had been second order, it would have been like a y equals x squared graph, so it would have looked sort of something like this. But it isn't either of those because it's first order, so it's just a straight line, and therefore the answer is A. Okay, question 9. All you have to remember is that partial pressure is equal to the total pressure times the mole fraction. That's the key relationship that you need for that. So it tells us that the total pressure is 250 atmospheres. And the mole fraction, well, the total moles, if we add them up, is 2.4 plus 1.2 is 3.6 plus 0.4. So we've got 4 moles altogether. So the mole fraction is equal to 0.4 over 4.0, which is 0.1 for sulfur trioxide. Okay, so it's just 250 times 0.1, which is obviously 25.0 atmospheres, and therefore the answer is B for question 9. Okay, question 10 wants us to find the pH of a buffer made by mixing those two. So remember, the key to any buffers question is Ka, which would be the concentration of the conjugate base times H plus divided by the acid, and all we need to do to rearrange that expression is just to slide these two terms around to get H plus on its own. So we get Ka times the acid divided by the conjugate base. Is equal to H plus. So all we've got to do is to work out what the concentrations of these are in the final mixture. So obviously they're not the same as their starting concentrations because each one's been diluted by the other one. So what we need to do is to work out the moles of each one and then divide those by the total volume to get these concentrations. Okay, so for this one we can do moles is concentration times volume, which is 2 times 0.2, which is 0.4 moles. And then for this one, again we've got moles is concentration times volume, which is equal to 1 times 0.6, which is 0.6 moles. And then to convert those into concentrations, we just have to divide by the total volume. So we've got 200 and 600 makes 800 cm cubed altogether. So if we divide by that total volume, we get the final concentration is moles over total volume, which is 0.4 over 0.8, because 800 cm cubed is 0.8 dm cubed, which is 0.5 moles per dm cubed. And then for this one we've got 0.6 moles, so the concentration is 0.6 over 0.8, which is 0.75 moles per dm cubed of the conjugate base. So we can plug those numbers into the expression. So that's equal to 1.32 times 10 to the minus 5 times 0.5 over 0.75, which is let's do that on the calculator. Okay, which comes to 8.8 times 10 to the minus 6 moles per dm cubed. And if we just take minus log of the answer, that comes to pH 5.06 is the number you get, which is answer C. So that's the correct answer. That looks like a lot of work, but of course you wouldn't have to write it all out neatly like you would in a normal question. So you could do that relatively quickly, But always bear in mind, if you tend to be a bit slow with the calculations, it's only 1 mark. So you can't afford to spend, 5 minutes doing that. So if you start it and it's going slowly, just, put a cross by it and think, right, I'll come back to that one later if I've got time. You cannot afford to spend, 5 minutes on a 1 mark question. That's a really important rule. But if you do all that, you can scribble it down quite quickly and reach that answer. So 5.06, which is answer C. Question 11 just wants us to calculate delta S for this reaction using these standard entropies. So remember, the thing to do is to add up the total entropy on each side. So on this one it's easy because all you've got is 1 mole of methanol, so it's just 239.7. On this side we've got 1 CO2, CO, sorry, not CO2. We've got 1 CO, so that's 197.6. And we've got 2 H2s, so we've got plus 2 lots of 130.6. So if you add those together, you get 458.8. So those are the total entropies on each side. And then you just remember that when the reaction happens, these substances are destroyed, so you lose their entropy. So delta S is going to be minus 458.8 because you're losing the entropy of the substances that are used up, and you're gaining this, so you're gaining its entropy, so it's plus 239.7, which comes to minus 219.1, and therefore the answer is A. In question 12, the quick way to answer this question is to remember that in a hydrogen-oxygen fuel cell, in any kind of fuel cell like that, the overall equation is the same as the combustion equation, because all that happens is that you get the same reaction overall as the combustion reaction. It's just that it occurs as 2 separate half reactions at the different electrodes rather than occurring directly, but that's the whole point about how fuel cells work. So the quick answer is to just think, oh yeah, hydrogen plus oxygen just react together to make water, and therefore the answer is D. It's, and if you're hurrying, that's the thing to do, but we can just go through and check that that's right. So remember that when you're given electrode potentials, the key word is RAP, which says reduction and positive go together. So this one is more positive, and therefore it's going to go in the reduction direction, which is the direction where electrons are gained. So this one is going to go this way, and therefore the top reaction is going to go in the oxidation direction, which is where electrons are lost. So it's going to go that way. So we just have to rewrite that top one with these things now on the left. So we have H2 plus 2OH minus goes to 2H2O plus 2E minus. And then we can combine those two together. The electrons, we've already got 2 in each, so we don't need to do any multiplying. We can just add them together directly. So we get half O2 plus H2 plus H2O plus 2OH minus goes to 2OH minus plus 2H2O. And then we do a bit of cancelling. You can see we've got 2OH minus on each side, so they cancel out. And we've got 1 water here and 2 there, so that's going to cancel. That's going to go down to 1, and we're left with a half O2 plus H2 goes to H2O, which is indeed answer D. So you could do it formally just to check if you weren't pressed for time, but remembering that these fuel cells just have the same effect as the combustion reaction would have been the quick way to get that correct answer. Right, question 13, we've got these 3 processes and we have to decide which ones are endothermic. So bond enthalpy of CH bond, well, bond enthalpy is the enthalpy change when you break 1 mole of bonds. You've got to remember that's the definition, and bond breaking is always endothermic. You always have to put energy in to break bonds, so the answer is 1 clearly is endothermic. So 1 we can say yes is endothermic. Second electron affinity of oxygen. So this is one of those oddities which you will have come across when we were looking at Born-Haber cycles and lattice enthalpies and things. So remember that electron affinity is when a mole of oxygen atoms each gain an electron to form an O- ion. That's the first electron affinity, and that one is exothermic because of the attraction of the electrons for the nuclei of the oxygen atom, and because this is attracted towards the oxygen, then it releases energy when they're allowed to come together. So that one is exothermic. But this is asking about the second electron affinity, which is this one. And you can see the problem now is that you're trying to attach a negatively charged electron to something that's already negatively charged. And the repulsion between those two charges means you have to put energy in to force them together. So that one will be endothermic, and therefore that one is also endothermic. So yes and yes for the first two. The third one, the standard enthalpy change of formation of magnesium. Well, enthalpy change of formation, remember, means formation from the element in its standard state. Well, magnesium is still an element, so its enthalpy change of formation is 0 because it's not changing, it's just staying as magnesium. So that one's not exothermic because it's 0, and therefore the answer is only 1 and 2 are endothermic, so the answer is B. Question 14 wants us to explain why reactions get quicker at high temperature, so it gives us 3 suggested things. So the first thing it suggests is that the activation energy decreases. So remember, that's not right. If you remember your Boltzmann distribution picture, the activation energy is a fixed value, okay, which you normally mark on there like that. And at least as far as we're concerned at A level, it doesn't change. So that's not decreasing, that's the fixed value. What changes as the temperature changes is the shape of the distribution. So remember, the higher temperature curve looks something like that, with the peak shifted further to the right and the whole thing spread out more like that. But the activation energy is what it is, so that one is clearly wrong. Collisions between molecules are more frequent. That's correct, because on average, what that curve shows you is that the molecules are on average travelling faster, and if they're travelling faster, they're going to hit each other more often, and therefore, because each time they hit each other, they have a chance of reacting, the rate will increase for that reason. So 2 is correct. But it's not the main reason. The main reason that the rate increases is this, that remember, it's the proportion of molecules that have an energy exceeding the activation energy, which is represented by that area. And that's what increases, because that relatively small area at low temperature represents a small proportion of molecules with enough energy to react when they collide. But at high temperature, it's a much bigger area, so there's a much higher probability of a reaction happening. So those are the 2 factors, and in fact that's the bigger one. So 2 and 3 are correct, 1 isn't, and therefore the answer is C. Question 15 is really a recall question on transition element chemistry. So that complex, you hopefully recognise that that's the formula of cisplatin, which if you draw it out looks like this. And you should know this because this specific compound is on the syllabus. So that's the cis isomer, and that indeed is a well-known compound because it's used as an anti-cancer drug. So statement 1 is correct. Statement 2 is not correct, because remember, this is a platinum 2+ complex. You can see that platinum's 2+, you've got 2 Cl minuses, and the ammonias are neutral, so overall the charge is 0. And platinum 2+ complexes are square planar, not tetrahedral. So therefore the bond angles, if that's a flat molecule, you can see the bond angle is 90 degrees, not 109.5, so 2 is wrong. It has optical isomers. No, it doesn't. What it has are cis-trans isomers, because that's the cis one. The trans one would be what you would get if you swapped those over, so that you put ammonia there and chlorine there, and that's now trans platin, because the similar ligands are now 180 degrees apart. So it has cis-trans isomers, but it can't have optical isomers because it's a flat molecule. The plane it's in is by definition a mirror plane, so it will be superimposable on its mirror image. You have to have octahedral complexes to get optical isomers. So therefore only statement 1 was correct, and therefore D is the correct answer.